Assalamualaikum warahmatullahi wabarakatuh. So this is our first video conference for JIF 418 for this academic year. So since this is our first, I might as well start with chapter 1. Okay, chapter 1 is about crystal properties and growth of semiconductor. So first of all, the topics in this chapter 1 is naming semiconductor. How do we name semiconductor? Because if you see there's a lot of different names attributed to semiconductor. If you look in your page 2 of your textbook, you'll see there's different how do we classify this semiconductor? What's a zinc and then gallium and then zinc sulfide, zinc selenide, and gallium phosphide. And how do we classify this one? How is this grouping being done? And why is it this one has only one element? So we need to at least have some idea, because from the name we are able to at least gauge the properties of it. In fact, if you look at the advertisement for handphones, I mean, there's on it says AMOLED. So what does AMOLED mean? AMOLED is actually amorphous light emitting diode. So from it, you know that it's made from amorphous. So amorphous material we use its property to classify it too. Okay, next in the topic of in chapter 1, there's semiconductor growth technique, because semiconductor doesn't exist in a pure state naturally, so we need to grow a purely semiconductor so that we would like to reduce as much as possible defect in our devices. So the basic fundamental of devices is the existence of semiconductor in a pure state. Physical properties. So what are the physical properties? What can we get from it? So basically, as I've told you just now, in the naming of semiconductor, first we would like to classify the semiconductor to have some idea of the physical and also optical properties of the semiconductor itself. And then under the topic of semiconductor growth technique, there will be the bulk single crystal, where basically the bulk single crystal, we are going to use it for substrate, that is the lower part of the devices. Or those of you who work in the semiconductor industry, the fabrication part, of course, you are going to use wafer. But wafer, we need to grow it, because wafer are bulk single crystal. So since bulk single crystal doesn't occur naturally in the so we have to grow it. Bulk single crystal is 100% pure crystal. Okay, next, apart from bulk single crystal as a substrate, we also use thin film epitaxial, where we grow thin film so that this part will contribute to our devices. So bulk single crystal is normally the bottom part of our devices, and thin film is where all devices are grown. So there are several techniques, common techniques that's been used for this device to grow the devices, which we are going to cover shortly if we have the time. Okay. Lastly, we were going to talk, if we have the time today, we will cover about the physical properties, basically what are the main semiconductor crystal structure, and also crystal defects, where crystal defects, the topic is missing in your textbook. But basically, I guess you have learned about crystal defect in JIF 104 in your first year. So if you have problems about it, please refer to your JIF 104 textbook, because over there, you learn more than you learn here, because over here it's just a revision for you. So that is basically the topic in chapter 1, naming semiconductor, semiconductor growth technique, and also physical properties. Okay, let's start with the first question. A name semiconductor, the one that you know. And just I type out, just in case if there's anyone around. Hello? Is there anyone in our class now? Okay, seems that there's no one around. Well, never mind. It seems that I'll be talking to myself. A name semiconductor, if you look in chapter 1, page 2, you'll see several semiconductor there. But basically, those in the semiconductor, of course, you did use silicon. Apart from silicon, depends on the material that you are making. If you are making LED, normally it's gallium based, gallium arsenide, or some other material. Or when in the olden days, mostly they used germanium. So, there are, this is what is the most common one being used in the early stages, and the one that's being used, gallium arsenide, are the one that's being used to make LED, or also gallium nitride, which is gaining popularity. Okay, so that's the naming of semiconductor, but I hope those of you at home can really answer it by yourself whenever that you go over this recording. At least try to recall it, because by knowing some of the names of semiconductor, you can learn to classify them, whether they belong to, rather than you have how to classify it, but you don't have any semiconductor material attached to each class of each category of the color classification. Let's when you go through this Webex conference, put the idea in your mind, the practicality of it, rather than just hearing it for knowledge sake. Perhaps, what you're going to learn today is related to your work, and please make it richer so that it really sinks into you. You can easily internalize it. Okay, since the naming of semiconductor, please fill up those blanks on a piece of paper, so at least you know a few semiconductor, so that you can regroup it into different classifications. Okay, to classify semiconductor, there are several ways. So what do you think? How should we classify this semiconductor? Any idea? All right. If you look at here, silicon, you can see that the silicon is not combined with any other element, whereas gallium arsenide is being combined with arsenic. And also gallium nitride is combined with another element, nitrogen. So from here, we can have some idea that, well, by looking at this, what comes to your mind? Isn't it? Because this is elemental and this is compound, isn't it? So we can classify our semiconductor based on its atomic composition, whether it's elemental or whether it's a combination of several elements or in a form of a compound. So if you look, from your experience every day, like gallium nitride, those that works in at ashram or where you are making light emitting devices, you know that most of your material is based on gallium. So, but why most of the other like transistors are being made of silicon? Because gallium-based semiconductor are normally light emitting. Depends on the band gap, and we can get different colors. So another property is we can just use the energy band gap of it. Because the colors that comes out from the gallium nitride is based on the transition from the conduction band that the electrons falls down to the valence band. So we have the extra energy which is emitted as light. So we can also classify it according to the energy band structure. And lastly, there are also, like I told you, more LED just now. And there are also, I cannot write it here because I don't have the symbol here. Polycrystalline, polycrystal. RYSTA, polycrystal silicon, let's say, or MOLED, like I told you just now. If MOLED means it is used amorphous material. Polycrystalline, this is, it is based on the crystal structure, because it's poly means many crystals. So we can also classify the semiconductor based on its atomic arrangement. And of course, single crystal, SINGLE, single crystal. For this MOLED, so it will MOLED, let's say, gallium nitride. So see now, yeah? Apart from we just knowing that it is a compound semiconductor, but if it's being, written like this, amor means it's amorphous, then you can know the structure of the semiconductor already by just looking at the name of the semiconductor. So, there's nothing great about amorphous. Actually, single crystal is the best. Second come polycrystal, and last it becomes amorphous. When the advertisement, it makes so, great that it's AMOLED, whereas we know that the efficiency of amorphous is much less than single crystal. So there's nothing to be, there's nothing great about amorphous LED. If it says it's single crystal LED, then that's the best. I mean, you know that it's efficient, the most efficient ones. Okay, so you see that by now, I hope, yeah, by just looking at the name, will at least give you what are the properties, the electrical properties of it. So that's why it's important for you to at least know how to classify the semiconductor based on its name. So let me reiterate. There's three ways for you to classify a semiconductor. Yeah, based on the atomic composition, based on the atomic arrangement, yeah, and also based on the energy band structure. Okay, under the classification of atomic composition, there's two types, as I've told you just now, elemental semiconductor and also compound semiconductor. Okay, compound means more than one. Okay, under compound semiconductor, you can also further classify the binary, ternary, or quaternary. Binary means 2, ternary means 3, quaternary means 4. Remember, quarter is 1/4, so it's four elements in it. And normally, LED has quaternary elements in it. Or it lasers too. Silicon carbide, normally we use it in IR detector because the band gap, yeah, it is not enough to emit light, but it's about heat, yeah, so it can become good IR detector. Zinc selenide is the old TV. I mean, perhaps the one that you have checked before, is zinc selenide, and gallium arsenide is the one that we use in making lasers and also LED. Okay. So apart from the number of elements, yeah, we can also classify it based on the purity of it. I mean, whether it's intrinsic semiconductor or whether it's extrinsic semiconductor. Intrinsic semiconductor means it's a pure semiconductor where it's not being doped, yeah? Whereas extrinsic semiconductor, it has been doped. What does it mean by doping? Is it by just adding material into an intrinsic semiconductor, make it doped, or what? It's very important for you to know what is the meaning of doping. Actually, extrinsic semiconductor has two groups, whether it is P-type or N-type. P-type or N-type. Whereas in P-type, P-type means there must be a vacancy in your semiconductor. Let's say, I have silicon here, but when I put in boron, if you look here in the periodic table, boron comes from group 3, whereas silicon is in group 4. So when you put in your boron into the lattice side of silicon, so there's one empty bonding site. So this one bonding site is called hole. It's not exactly whole, literally physical, but it's a missing bond here. So if we have many of this boron that's being embedded at the lattice side of the silicon, then we have a lot of holes where these holes are actually charge carriers in a semiconductor. Different from in metal, the charge carriers are electrons. But in semiconductor, there's another charge carrier called holes, which is essentially empty bond sites. Empty bond sites, which is called holes. It's not physically whole, but empty bond sites. So if we look here again at the periodic table, if you put in aluminium into the silicon, at the lattice side of silicon atom, then you will also get the empty bond sites, which will act as holes, which will act as charge carriers. So, I've used this acronym over the years, so that it's easier for you to remember. So, if you put in, if you doped your material, say from group 4 with boron, aluminium, gallium, and indium, what you are going to get is holes, holes charge carriers. Or we say bagi, isn't it? B-A-G-I, bagi. So we just use this acronym to remember it. So doping group 4 with bagi group 3 will give you P-type semiconductor. But the thing is, the element from group 3 that you put in your semiconductor must replace the silicon atom at its lattice side. But if your boron atom stays, let me draw it so that it's easier for you to get it. If your boron atom stays interstitial somewhere here, so this means the boron atom now, the red boron atom, is not doped into your material. Doping means it must replace your silicon atom. See, this is silicon atom, but now the boron is at the lattice side of your silicon atom. It replaces it. But if it is interstitial like this, then this is not doping. All right. It has to be at the lattice side in order for you to get these extra charge carriers. Okay. So the extra charge carriers, this one, empty bond sites will only occur when your dopant atom replaces the atom, the host atom. I hope you understand what does it mean by doping now. Okay, let's move on. Okay, now, what about N-type? So what element should we add? What element should replace your silicon atom? If P-type, we doped with group 3 dopant. So if you would like to have extra electron, this extra electron, extra charge carriers now, we need to have a free electron, then naturally we have to dope it with group 4, isn't it? Because group 4 has one extra atom, one extra electron compared to group. We need to use the group 5, because group 5 elements have one extra electron compared to group 4. See? But the condition of it being at the lattice side or atomic side also holds. Okay, it must be at the lattice side. Replacing the silicon atom. But now, since silicon atoms has only 4 bonding sites, so we have one extra electron that's going to contribute towards conductivity, electrical conductivity. So, in intrinsic semiconductor, we have holes as charge carriers, majority charge carriers in P-type silicon, and in N-type silicon, we have extra electrons. So, what are the conditions for a semiconductor to be doped? First, it must replace the host atom, not in the interstitial. Second, it must be the JIF holes or JIF electron. Depends. If you like to have more majority electrons N-type, so you choose group 5. If you like to have holes as the majority carriers, you choose group 3, yaitu bagi pas. But for N, pas. Phosphorus, arsenic, antimony. Phosphorus, arsenic, and antimony. Senang saja. I mean, it's easier for you to remember, isn't it now? Bagi, pas. Bagi is P-type and pas is N-type. Okay. I hope it's clear now for you, what does it mean by doping? So there are 2 conditions for doping a semiconductor, 1 and 2. Okay, let's move on. So that is the based on a classification based on atomic composition. So it's either elemental or compound, yeah, based on the number of semiconductor in it, based on the number of element in it, and also based on its purity. Okay, let's have a short review of what we have talked before. Just now, we just discussed about naming or classifying semiconductor based on its atomic composition, where basically under that topic, there's two ways of classifying under atomic composition based on the number of elements and also based on the purity. So if we look at this one, silicon carbide, so under atomic composition, we know that it is a compound semiconductor. Germanium is since this one is the only one element, so it's an elemental semiconductor. Zinc sulfide, so since there's two elements in it, so this is compound, pure compound. But this is P germanium arsenic, P gallium arsenide. So P means it's P type. So this is extrinsic semiconductor. And of course, GE, since there's only one element, so this is elemental. Okay, there's another question. I mean, what we have talked just now, yeah? What is the difference between intrinsic and extrinsic semiconductor? So I guess I've left this question for you as your Webex, first Webex assignment. I hope I will upload it on Monday for you to fill it up, yeah, and send it to me. I think now I give you 2 weeks to answer this question. Okay, I guess we are done with classification under atomic composition. Next, we are going into atomic arrangement. And there are 3 types of atomic arrangements, like I told you just now, yeah? But never mind, let's review it again. Yeah, whether it's single crystal, poly means many, and amorphous. Remember the amor LED? Okay. Single crystal, what's the difference between these 3? Single crystal is periodic. If you look here, you can see, I mean, the arrangement is repeated, yeah, in the long range. This is the same everywhere, repeatedly, yeah, so it is periodic. Normally, the common semiconductor that we use, single crystal, is cubic shape, but there are also HCP, hexagonal closed pack, but most of them are cubic anyway. And polycrystal means there's many crystals. If you look here, yeah, different colors. This is one crystal. The one darker is another crystal. The lighter blue is another crystal. Yeah, if this one is one big crystal. Yeah? But this one consists of many crystal. Polycrystal. Poly means many, isn't it? So it's just by the name of it. And at times, it's being written by using this symbol, micron. It says like that, silicon. So you know that this is polycrystal. Okay. So polycrystal, if you look here, this is one crystal. So this is one crystal by itself. This is the grain. And this is another crystal. So this is 1, 2, and 3. Compared to this one is all one crystal. One crystal. But consists of smaller units, of cubic arrangements of it. But this is one big crystal, but this one is 1, 2, and 3 crystals. But if you again look at this one, the periodicity, you see this one is all horizontal, but this one is vertically arranged. But this one is a bit slanting. So you see that the periodicity ends at the grain boundary, at the grain. So this is called grain. Boundary is called grain. So the periodicity ends at the boundary. Okay, periodicity stops at crystal grain. So, but this one is periodic all throughout. But this one, it stops at the crystal grain, after all the grain boundary. Okay, what about amorphous? Any idea? Okay, amorphous basically, if you look here, the arrangement, at times there's linkages 1, 2, 3, 4, 5, and then at times, and then over here is 1, 2, 3, 4, 5, and then this one, you see 1, 2, 3, 4. I mean, there's the periodicity, there's hardly any periodicity. So no periodic structure or short range order, perhaps it's just small. Say 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 over here, but not the rest. Yeah. So no exact, basically no periodic structure. So amorphous, no. Poly, many. Single crystal, one periodicity. I mean, one crystal, periodic throughout. Periodic stops at crystal grain, no periodic structure. Simple, isn't it? Okay. Okay, look at it for a while and then at least you get some idea. Periodic only until crystal grain, and no periodic at all. Isn't it? Easy to remember. If you make it in the form of a line, so you can see, okay, periodic, single crystal. Periodicity stops at grain boundary, poly. No periodicity, amorphous, isn't it? I mean, if you can just okay, sorry. Okay, the one just now. you can just make a line or something like that. Fine. Okay, make a line like that. Yep. No. Okay. So here, green boundary. Fine. So this is amorphous. This is poly. This is single. Okay. So easy, isn't it? Just remember, no periodicity, stops at green boundary, and periodic. Amo, poly, single. Just remember that, you are fine. I mean, try to learn to make something like this, yeah, for your studies. Try to simplify things rather than let things um, um, in its separate compartments or something like that. So if you look this one, so you can see the trend of how things changes. So it's just one generalization. So you just remember all this, you are already safe. Learn to do like this kind of learning strategy. Okay, name 3 types of semiconductor atomic arrangements. Of course, you should know by now, isn't it? There's 3, isn't it? 3. So it's single, poly, and amorphous. And state their structural differences. Okay, I'll put this one as one of your Webex conference second question. Okay. Okay, let's go to the third classification, yeah? So the third classification is based on the energy band gap structure. So basically there are 2, yeah, whether it's direct semiconductor or indirect semiconductor. So direct semiconductor produce visible light, yeah, like your LEDs, and indirect doesn't produce visible light because direct semiconductor is able to produce visible light because the top of the bottom part of the conduction band lies in the same vertical position as the top of the valence band. So whenever the electrons fall down to the valence band, the energy that's being given out, or the energy gap, is sufficient, being sufficient to produce visible light. The gap here, the energy in the gap here, is falls in the visible region of the electromagnetic waves. So we are able to see the color, visible light. However, yeah, visible spectrum, because the energy in it, yeah, fall in this region. So we are able to see it. But yeah, for in the indirect semiconductor, normally the energy is not sufficient to reach a visible spectrum. Normally it's around the infrared region. Infrared means it's a heat, yeah. The energy is not enough, yeah, to reach the visible spectrum. If you, in terms of energy, in terms of energy, the energy is higher as you go from infrared to ultraviolet. Higher. So, if this gap gives HV, where the HV falls in the invisible region, visible spectrum, then we are able to see it. So that's your LED, visible. However, here, you see here, if red has a smaller B gap, because the energy is red, and then yellow here. So red has a much smaller energy than yellow light. So the energy gap is smaller than the yellow LED light. Yellow LED. See, the gap is much larger, so that it will, when it moves from the connection band to the valence band, so it gives a much larger energy, which is essentially yellow light. So this one is less, so the gap is much smaller. So that's the difference. So normally we can put material in it. So we can manipulate your LED by putting other element into it, so that you can produce yellow light, you can produce red light, and you can produce blue LED. So it's possible for you to manipulate your gap, so that you are able to produce the colors that you need. Okay. And as for the indirect semiconductor, I will show you. As for the indirect semiconductor, okay, if you look now, you see that compared to the direct semiconductor, the lower part, the lowest part of the valence of the conduction band is not at the same vertical axis as the top of the valence band. So we need to have some intermediate position, level, for it to, so the electron need to move up to this level first, and then only goes down to the valence band. If you compare to the one here, the energy that's being given out is much less than before. So, and this energy that's being given out is normally in the infrared region for the case of silicon. So this energy is being lost to the lattice, but only this one is being given out. Normally, as I've told you just now, in the case of silicon, this will be infrared. Or in layman's term, it produces heat. Okay, it produces heat. So it's just that, by manipulating the material that you put inside a semiconductor, you are able to produce material, whether it's direct or indirect semiconductor. So from there, you know that, well, this one will able to produce visible light because the band gap, lies, the band gap that's here will give out energy that lies in the visible region. But if for this case, you know that definitely, for indirect semiconductor, since it has to do two kind of transition, so it won't be able to produce in the visible produce energy in the visible region, but only ones that can produce heat, which is insufficient to reach the visible spectrum. Okay, so basically that's the topic of classification of semiconductor. And I guess we don't have time to go into semiconductor growth technique and physical properties. So I hope you just read the one in our textbook and try to understand it. I guess it's not that difficult because you just need the procedure of how it's being grown, and then you just go along with it. Oh, here's another question about this energy band structure. Of course, we have discussed this now, two types of semiconductor, based on the energy band structure, direct and indirect. And of course, there's another one, state their differences. Again, to answer this question, I will put up as your third question in your first Webex assignment. So, as I've told you just now, please, hand in or upload. I will put a button there for you to upload your assignment need. But this time I give you only 2 weeks to do it. Since it's pretty simple because it's just based on our Webex conference. Should you have any question about this topic, please just email me. Okay, all the best to you, and remember that we have another one, another 2 more, if I'm not mistaken, before the intensive course in January. Please, I beg you, please do come to the Webex conference so that it's easy for me to know where your problems lies. If like this, I just tell you, but I don't really know whether you understand or not, please do come to our next Webex conference. Okay, thank you very much. Please, as I've said before, do contact me if you have any problems. Okay, thank you. Goodbye.